Hello, today I will introduce our work, Neural-Centric Video Processing Pipeline for Unified Multitask Inference. The main motivation is that video processing is shifting from human-centric consumption to machine-centric inference. However, current video analytics pipelines still follow a human-centric design. Videos are encoded with traditional codecs, decoded into RGB frames, preprocessed, and then passed into neural networks. This design introduces three inefficiencies. First, full RGB decoding and early feature extraction are repeated for every downstream task. Second, traditional codecs are not differentiable, so the video representation cannot be optimized directly with task objectives. Third, random access and preprocessing create system bottlenecks, especially when only a subset of frames is needed. These inefficiencies become more serious when multiple tasks run on the same video. Our goal is to build an AI native media representation. Instead of using one representation for human visualization and separate pipelines for machine inference, we want a single shared representation that can support all various tasks. The key idea is to generate task-specific neural features directly without reconstructing full RGB frames for every task. To do this, we use implicit neural representations or INRs. INR is a paradigm that represents data as a continuous function parameterized by a neural network. Our key observation is that NeRF-style video INRs decode frames in a coarse-to-fine hierarchy. The intermediate features in this decoder already contain useful visual information. Since downstream DNNs also process visual information hierarchically, we can reuse INR intermediate features as inputs to downstream models. This allows us to skip explicit pixel reconstruction and redundant early feature extraction. Based on this observation, we propose NVP, a neural-centric video pipeline. NVP consists of two phases, an encoding phase and an inference phase. In the encoding phase, MVP prepares a neural video representation and task-specific connection to downstream models. In the inference phase, it partially decodes the representation and directly injects features into pre-trained backbone. In the encoding phase, we first train an INR to represent the video, and this INR becomes the front end of the pipeline. It can still reconstruct video frames for visualization, but more importantly, it's intermediate layer to provide neural features that can be used for machine tests. The next question is where to connect the INR to each downstream model. MVP solves this using CKA-based representation selection. We compute the similarity between INR intermediate features and the layers of a pre-trained backbone. High CKA score means the two layers encode similar information. Therefore, MVP keeps only the top-ranked layer pairs as candidates instead of exhaustively testing every possible connection. This representation selection efficient while still finding near optimal layer pairs. After selecting the layer pair, MVP trains a micro adapter. The adapter maps INR features into the feature space expected by the frozen pre-trained backbone. It's a lightweight, so adding new text only requires training small adapters rather than retraining the whole model. And also because the entire representation is neural, we can also perform end-to-end optimization. At inference time, MVP performs partial decoding. For each task, it decodes only up to the selected INR layer, applies the corresponding adapter, and skips both full frame reconstruction and early backbone layers. For multiple tasks, shared INR computation can be reused, which further reduces redundant processing. Now I will summarize the evaluation results. For latency, MVP achieves up to 89% lower latency 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 compared to the CPU codec pipeline, and up to 78% low latency compared to full INR decoding. Across classification, action recognition, object detection, and captioning, MVP consistently reduces total processing time while maintaining comparable task accuracy. In several classification settings, MVP even improves accuracy over the traditional pipeline. The overhead breakdown shows that traditional preprocessing is a major bottleneck. MVP removes the most of this cost by avoiding full RGB frame loading, resizing, transformation, and GPU transfer. For bitrate versus accuracy, MVP achieves similar or better task performance at lower bit per pixel than H.264. For encoding efficiency, MVP adds only modest overhead compared to INR training. For CKA-based selection, the selected top layer pairs achieve near optimal accuracy. For adapter efficiency, all micro adapters add less than 1% extra parameters compared to the pre-trained backbones. This makes MVP scalable to many tasks. In conclusion, MVP replaces a traditional decode and extract pipeline with a neural-centric pipeline. By using INR intermediate features, CKA-based selection, and lightweight adapters, MVP enables unified multitask inference with lower latency, lower computation, compact representation, and compatibility with pre-trained models. Thank you.